Uh, shall we start, Ashutosh? Mr. Ji?
Yes, sir. Sure. Sure, sir. Can you see the slides?
I can see your slides, yes.
Okay. Should I start?
Yeah, let's make it for half an hour, right? So maybe at 11:30 we'll start a short panel discussion, then some other formalities. So by 12 o'clock we should be able to sum up.
I will try to finish as soon as possible.
No, don't go as soon as possible. We'll go by make it by 11:30 or so. Huh? Okay. Please go ahead.
So the today's talk is about AI for autonomous vehicles, and Professor Kim has already told you people in much detail. So I would like to start the presentation from the introduction of my lab. So in this presentation, we will see the research ramifications we have in our lab. So first we will see the end-to-end steering control, and then I would like to share some demonstration which we have demonstrated at Seoul Smart Mobility Expo, and then we will go for the smartphone app-based sharing service in autonomous vehicles, which we have developed with the SKT company and Yonsei University. And then I would like to showcase the development of 5G network-based intelligent management server platform for commercial vehicles. It was the project given by Acetel, which is one of the localization-based company. And it was for the mobile CCTV. We will see in further slides. And then I would like to go through with the details of irregular situation autonomous vehicles on which I am currently working on. So this is the brief introduction of our lab, which Professor has already told you people. So we have right now 3 autonomous vehicles. The first vehicle was in 2012, which was equipped with the differential GPS system, LiDAR, camera, LabVIEW, PC, and tracking pre-planned path. The second vehicle was purchased in 2015, which is equipped with the camera, LiDAR, radar, and it has NVIDIA general graphical processing unit, GPU PX2, and it has end-to-end steering for learning-based modules. And then our third vehicle was purchased in 2018, which is also equipped with the camera, LiDAR, radar, and it has Linux PC and the neural processing unit, on which we can train and inference different kind of models we are going through. And it is based on the learning-based control as well. So the vehicles are equipped with different sensors. The main sensors we can talk about the different equipments like the NVIDIA Drive PX2. It is an open AI car computing platform which combines the deep learning sensor fusion and the surrounding vision. And we have the IBO LUX 4 level scanner and 8 level scanner, which is the LiDAR sensor which supports the object classification and tracking. And it allows the environment in field view of 110 degree. And then we have the Navatel GPS, which is a high precision GPS with the original equipment manufacturer, and it supports different kind of GPS techniques. And the autonomous vehicle is equipped with the cameras, which supports the advanced driver assistance system, and it supports the connectivity with NVIDIA tools as well. Then we have IMU, which is for the inertial sensor. It has a set of 3 gyroscopes, 3 accelerometers, 3 magnetometers, and temperature sensors. And it can compute precisely 3D orientation of the vehicle. Then we have the Delphi radar 2.5, which has wide field view and the mid-range, which can cover the long and mid-range coverage. So I would like to share the video. Can you see the video? Hello, Professor? Hello? Yeah. Hello?
No, sir. Right now,
Yeah.
we can't see.
Uh, uh, I'm sharing the video. Is it visible?
So not yet.
Okay.
It's not played actually.
Yeah, your screen is displayed, but the video has not opened yet.
Let me see.
I think it's not played in your system itself, right?
No. In my system, it is playing.
But just we can see your. Okay.
You are in the full screen mode.
Which-
If you exit full
Yeah.
screen mode is broken,
Okay.
you must reshare.
Again.
Okay.
Okay.
So you did not share your whole screen, or you might have shared one window.
I have shared whole screen, but video is not running.
Restart.
So which particular video player you are using right now?
The Microsoft.
Big bug. Micro bug. You can share instead of. Now it's okay?
Yeah, we can see your slides.
Okay.
Yes.
Yeah. Then you share this screen instead of.
But video is not playing actually.
Let's play it.
It's okay.
Okay. So right now, is it visible to you people, the video?
Yeah, we can see it. Yes.
Okay. So in this video, as I already explained that we have 3 autonomous vehicles. So this video is portraying the demonstration which was captured at one city, and the lap was around 2.4 kilometers, and the vehicle was capable to move with the 30 kilometer per hour speed. You can see here the descriptions are there, and total area was 24 kilometer covered. So this is the lap. In your video screen you can see the lap covered, which is at the Sehong city at Korea. This is the lap. It is around 2.4 kilometer, and total distance covered was around 24 kilometer. And this was the vehicle, which is equipped with different sensor we have just talked about. So this is the real-time video captured on that same lap. This is the video showing from the another vehicle, and this is the main autonomous vehicle. Then later on we will see the this is the black box video which was captured through the vehicle. This is the original video frames we are capturing. These are the logs, and here we can see there is one window for black and white binary video. This is the path we are going on, because here in Korea it is the left driving track, and this is the screen where we can see and sense the coming vehicles and obstacles, etc. So as we can see that we are moving, and there is one bus which is coming, so we can see in that video it will be detected. Yeah, you can see. It stops. Okay. So here we can see the bus is there, which is captured with the bounding boxes. And this is the captured green bus and other vehicles we can see. Yeah, again there is green box. So this was the brief description of our lab. Then we will go with the next slide for the end-to-end steering control. So this was published in a paper in the IV Intelligent Vehicle Symposium in 2018. And the concept is related to the DARPA autonomous vehicle DAPT system. So basically the DAPT system has one NVIDIA driver PX2 which supports different camera like left camera, center camera and right camera, and it has a CAN bus through which we can see the steering wheel angle, and we can control our vehicle, and it has the connectivity with the external solid drive through which we can put our database for inference and training purposes. So the concept is related to as explained by the professor in previous session. There is the model, CNN model, which can see the actual adjustment and shift of the steering wheel, and after capturing the screen, the video and image visual sensors from the different camera sensors we can predict what should be the exact steering for our vehicle, and if there will be some error, then through the back propagation we can adjust that error so that we can go for the exact steering angle we require. And this is the basic concept of our DAPT system, which was from the NVIDIA, but we have proposed DAPT with two training phases: pre-training and post-training. Post-training is the reinforced training. The pre-training was actually from the pre-scan, which is a simulator which only simulates the virtual scenario situation, but we have adopted the pre-scan model and we have retrained that model with our own network. That network was this. It has 5 convolution layers, as we can see. Convolution layer 1, 2, 3, 4 and 5, and it has 3 normalization layers, batch normalization, and then it has 2 fully connected flat layers. Finally, at the output we are able to predict the steering wheel angle. So the whole system works like there will be the visual sensor through which we will capture the video images and the real-time frames, and then our DAPT model will predict the value of the steering angle, and then accordingly the vehicle can move, as we have seen in our previous demonstration. So we have captured the input at the frame size of 160 cross 90 in RGB frame. So this is the track we have chosen for testing and training. Already professor has told you people that the training direction was in counterclockwise and testing was in the clockwise. It was just to preserve that the training and testing inputs are totally different. They are not same for the model, so we can avoid any kind of overfitting or cramming situations. And we have different like curved road and straight road kind of scenarios in our lab chosen, and this lab is actually at the Yonsei University. So we can see the scenario is like there will be the ego vehicle, which is the autonomous vehicle on which we have implemented this DAPT system, and there will be some front vehicle. So there might be 2 scenarios, that in the front there is no vehicle like we can see in figure B, and if there is a vehicle, so what is the minimum distance through which we can estimate the exact angle. So we have chosen the minimum distance at 8 meter and 10 meter, and we will see the results in future slides. So basically there are two kind of scenario: the fully observable scenario and the partially observable scenario. So these are the experimental route which we have seen, and these are the results. So we can see that the pre-training model, that is from the pre-scan, it has problem while there is some sharp turn or something. It took the lane departure if there is some sharp turn, so it was not able to turn at the it was not able to predict the steering angle at the sharp turns. But the post training model was crisply identified the steering wheel angle, and it followed the track. So, and again, if there was scenario for the fully observable and partially observable, for fully observable we can see the pre-training and the post-training was applied, and the pre-training was already taken the lane departure after a few frames, but the through the post-training model we have again found the same track. But in case of the partially observable circumstances, for 8 meter there was some lane departure, but for 10 meter we have easily gone through in both cases. So in this way we have developed our own end-to-end steering control, which was able to follow the exact steering wheel angle. These are the videos. So this is the track we have followed. It is the inside the Yonsei campus. See, the vehicle has good steering wheel prediction, so it turns. Now there is the parking place where the vehicle will again take the turn and safely park. This is the position of parking where vehicle will park itself. This is the parking position, and then again it will retrace the lap after a few times. Again there is turning, and successfully it turns. So through this demonstration, we have seen the vehicle was able to predict the steering control at the sharp turning as well, and it was able to park itself at the desired location. Again it turns. and retrace the path. Yeah. In the next video, we can see the valet parking at the ground level. So it is the automatic parking scenario. See, safely the vehicle was able to park itself at the underground basement. These are the simulation results which you have already seen in previous session. So here the first screen is showing the steering wheel control for the pre-driver mode, and this is our proposed CNN model through which the DAPT sky system was developed to predict the angle. So here we can see the pink line is showing our own model, and the yellow line is showing the previously trained model. There is sharp turn and there is lane departure. The vehicle in the pre-trained model was not able, it was failed to take the turn, but in our own trained model in the simulated environment, the vehicle was able to safely took the decision. So in the real scenario and in the simulated domain, the model was able to predict the steering wheel angle correctly. And again, there is a test. Previous video was at the lesser speed, and for the faster speed, this video will show. This is the map of the lab. You can see at the bump, the vehicle has some jerk. See, there is a turn, so it takes right turn safely. And then maintain the lane. Yeah, there is a left turn. So it took the left turn safely and then maintained the lane. Again, it was just because U-turn was not trained in our model, so it was the manually taken turn. And then now vehicle is passing through the underground. It is able to follow the lane safely. So we have, as I told, that we have developed the end-to-end steering control for the autonomous vehicle and demonstrated the same for the simulated environment as well as the real environment. Now in second demonstration, we will go with the Smart Mobility Expo, where this expo was basically for the conference and exhibition and experience, and the theme was freedom for mobility, where different participants have participated from the globe, and the expo was mainly for the autonomous driving, for ground vehicle, for urban air mobility, and for the personal vehicle. So the expo was related to the autonomous bus shuttle, the drone taxis, and the personal vehicles as well. and it was having delivery bot as well. This is the delivery bot, this is the minibus shuttle, and these are the lab for the personal mobile track. These are the drones taxis. So we have experienced these scenarios, and we have demonstrated our own vehicle in this scenario as well. And this is the slide of our own vehicle, and the video is taken from the another vehicle. So this is the autonomous our autonomous vehicle, which is third generation vehicle, and the video is captured from the another vehicle. So it is running in the autonomous driving mode. And these are the real road on the city. It is the Sangam test bed, which is developed for test bed for the autonomous driving task itself in Seoul, capital of South Korea. See here, it stops at parking. At the traffic light, because I told you here it is right. Always right turn is open because it is the left turn control here. So we can easily violate the traffic signal while we are turning towards right. As in our country, in India, we can move to the left, but yeah, here it goes because of the green signal. Because of time limit, I am just skipping and showing the main frames of the video capture. See here, you can see that it stops because you will see there is the round turn and it has to go right. It should be open, but you can see there is a pedestrian passing, so it stops here until the pedestrian goes, and then it took the turn. Otherwise, because it was the right turn, it should go directly, but the vehicle was trained to stop for the pedestrian. So the next video is the same shoot from the Ego vehicle itself. If time permits, then I will show the video, otherwise I will skip that, because it is the same video just taken from the Ego vehicle, means the autonomous vehicle itself. So should I show the video or I should go ahead?
You can show it. It's not a problem.
Okay. Is it visible? Is it visible at the screen?
Yeah, it's visible.
Yeah. So the video is taken from the autonomous vehicle itself. So here for the left turn, it stops and it predicts the decision through the traffic signal. Yeah, now you can see it predicts the left turn through the traffic signal, and it took the turn. There was because of the other vehicles, it just touches the side vehicle. Now it is able to follow the lane.
Actually, there's the free text environment in San Francisco. Actually, you can receive the whole traffic line information by air. You know, when the trains in.
Yeah. Because the vehicle has to take the turn, and this green light is for the front vehicles, foregoing vehicles. So it stops. See, again for the left turn, it will take the turn correctly. Now it maintains the lane because there were the standing vehicle, but it was able to predict them and maintain the lane. Now for foregoing, it adapted according to the traffic signal. We can see it predicts the bump and take the decision. It predicts, yeah, here it is the same place. In previous video, we have seen there was one pedestrian for which the vehicle was standing. So this is about the demonstration of the autonomous vehicle which we have demonstrated at the exhibition at the Seoul Smart Mobility Expo. Now we will back to our slide. Yeah. So the next example of our research was for the smartphone based car sharing service in autonomous vehicles. So we have implemented very good concept, which is for the what three words. I will explain in future slide. It is actually to provide the precise location of the location information. So in the app we can see that there is a person asking for the car sharing vehicle, and it says that I'm standing here through the yellow dot, and through his app view it says that the taxi number, suppose 1234, is coming within 6 minutes. So the requested taxi will come to that place, but at the app view of the driver, it asks for the user that where you are asking to for me to come, is it able to stop there, because we know that we cannot stop right now at any place. So if it will search for the location, if the location which is asked by the user is available for stopping, then it will go. Otherwise it will ask for the new location, then the user has to search the new location where the vehicle can stop. Like in the green spot we can see here there is a place to stop, and the previous yellow spot was not here, it was not able to park the vehicle because it was the main road. So the user will ask for the new location where the autonomous vehicle can stop itself. So it will be updated and then sent back to the vehicle, and according to that vehicle will come. This was the concept which we have developed in our app. So this is the conceptual diagram. Here it is the sole main control unit through which we can the officers can monitor, can trace each and everything, and it is well connected with the cloud. So the end user will be connected to the cloud, and it will ask for some car sharing, and there will be different autonomous car shareable autonomous vehicles. They will be connected through the control unit. So when the user will ask through the cloud, the information will be processed from the control center to the nearest possible vehicle. And these vehicles are able to share the information related to the real-time information related to the traffic, related to the signal, related to the accident, or if vehicle has some problem, it is under the some there is some wear and tear or some problem in the vehicle, so it will update its current scenario in real time, and it will be able to provide the information of construction, ongoing construction, or the possible location of stop at the real time through the onboard equipment, onboard unit of the vehicle to the control unit. So we have developed this smartphone app. So this is the what three word I'm talking about. This is actually creating a grid of 3x3 meter, and this grid is located in 3 words. Like for example, we can see this is the actual, the below layer is the actual map, and this is in the grid of 3x3, and there are 3 words. Like for this grid, we can see there is the word social, attending, and dive. So what it does, it actually bifurcate, it actually break the actual land in 3x3 meters, so then we can find the exact location. Suppose we are sitting somewhere, then these are the 3 meter cross 3 meter grid where we can ask, we can share this location in terms of 3 word, and we can follow that 3 word to locate the precise location. So we have just implemented this 3 word concept in our vehicle, as I have just demonstrated in previous slide. So through this what 3, and this is the view of the control unit at the SOL. So here we can see they can monitor each and everything about the track, the current going situation, and inside the vehicle as well. So these are the cameras through which we can see the inside of the vehicle, outside of the vehicle, road, and there are different CCTV monitors. So at the monitoring center, one can see each and everything. And this is the another view of the vehicle control center. They can see these vehicles are on their way, and there will be 4 status. One is for booked, and then vehicle will show the on way to pick up, and another is if vehicle is already occupied, so it will say that it is in use. If vehicle is idle, so it will say the status as idle. If vehicle has some problem with the battery or it is requiring maintenance, then it will show the status as the out of service. This is the media coverage for the same.
Slide.
Yeah, professor has just demonstrated this to the YTN Science channel for media coverage. So the another example is related to the development of 5G network-based intelligent management server platform for commercial vehicle. It was the project by the Acetel and Johnson University. The Acetel is a company which provides services at the location-based service platform, bus information system, artificial intelligence, and Internet of Things. It is very big location information providing company in Korea. And it provides the black box unit, which is the onboard device unit, onboard device equipment with the most of the vehicle running either for level 2, level 3, level 4, or level 5. So we have done one project through this SATL, and the project was related. Our task was related to the road condition recognition, accidental and event recognition on road, license plate recognition. This was the very interesting task because we know that sometime there is some threat or some theft related to the vehicle. Some vehicle has been theft. So if we are able to see the license plate in recognition in real time, so it will be very easy to get the surveillance. Just put the ID number of the vehicle which was theft by someone, and then on the real time basis we can monitor that these vehicles are going around on this location. So we can match the theft vehicle, and we can identify that its current location is here, and we can easily go for that. So for this we have developed a CCTV in motion, which is mobile CCTV. It was based on 5G platform. So the main concept was that the onboard equipment will be enabled with the 5G technology, and it will be working as the motion CCTV in motion. So in this way we can solve many issues like the real-time traffic in each direction, the foregoing true and foregoing lanes, and we can recognize the license plate in real time. We can recognize the road and accident on the real time basis, and we can recognize the road condition. There is pothole, there is some construction going on, or what is there going on. So we have gone through this project, and the concept is like this for the commercial mobile CCTV, that there will be a consumer having the SATL mobile CCTV app, through which it will be connected through the control centers, and this control center will be connected on the 5G network, and it can communicate through the satellite GPS location, and it can see the real-time location and information and process this information to the end user. So we have showcased one case here that one person is asking through his mobile phone the location of traffic for the Daejeon city, which is a city in Korea. So this request has been processed from the app to the control unit, and then control unit asks to the taxis which are running there at the Daejeon station, at the Daejeon city, for asking them to give the real time their video at the Dejan city, so that the end user can get the real time traffic information at the Dejan city. So this information will be sent back to the control center, and from the control center end user will get the same information, and he or she will be able to monitor the real traffic scenarios using this app. So in this project we have developed the deep neural network model, which will be implemented on the onboard device, and there will be the commercial vehicle black box through which we will capture the real-time video, and through this video it will be the input for the network we have trained, and then it will
Dr. Mishra,
yeah, can I
it will
go?
be great if you can summarize within 8 minutes, maybe by 11:30, right?
Okay, I will try my best.
So that we
So,
can have another discussion, right?
yeah, we can see that there are potholes, there are accident, there are another road damage condition, and other. Yeah, this is the ID plate, license plate detection in real time. I was talking about. So we have done this. So you can see the video from the black box. The video images are capturing the ID plate and locating this, and the onboard device was through the rock chip. So this device was able to capture the identity license plate, ID plate in real time. So we have used the Tesseract, which is the optical character recognition engine, and we have used the OpenCV, applying the contour recognition, cropping, Gaussian blurring, and other techniques, adaptive thresholding, etc. And we have developed our own model. These are the results. So we know that the YOLO has very version of YOLO 1, 2, 3, and 4, but they are very bulky. So we have created the tiny YOLO, which can be suitable for the onboard device, and we have used the transfer learning concept. So we train and just use the inference information for the real-time capturing. These are the results which are showing that on the real time we can see the crack with the location, with the real time information, and these are the images for that. Again, there is a road accident damage, and there is some construction or any location which shows that one-way traffic or anything is there. So we can able to see the same scenario in our real-time network, real-time trained onboard device, and it shows the location as well. So yeah, it was the project we have gone through, and we have successfully completed that. Now, this is the irregular situation in AV, which may be in the level 4 and beyond. Professor has already talked about that. There are many scenarios. So I am not going in detail. I'm just going through the what we have done in our project. So as the NHTSA, the National Highway Traffic Safety Administration, says that the level 5 is a vehicle which can do the automated driving task, and the passengers will be only the occupant. They will not contribute themselves as the driver. So the problem is that there will be no driver, no in charge, only every passenger will be occupant. So who will take care of the security and safety? Because security and safety is the main issue in that case. And security is related to the vehicle itself, because the passenger can wear and tear the vehicle and provide some harm to vehicle, and security to the passenger itself, because as professor said that there will be privacy issue and other things. We will go in detail in the future slides as well. And for safety, because it is related to the safety that somebody has a hand or head outside the vehicle, so there is no in charge who will take care of that. So we have done all these things, considered these things. So mainly we will have the security and safety related to the occupant and safety related to the vehicle. So as already professor discussed, that first question is where should place the camera? What should be the proper positioning of the camera? Should we place here or there or at the center? So the best choice will be the single shot image at the center, because here we can see entire vehicle in single slot, but it has future bottlenecks we will see. So we have said that just train our model depending upon this single slot image, and it will be the best position for the AI camera, and then just use the inference of this trained model for the real-time scenario. But what I was talking about the aspect. So there will be two cases. This is the front view positioning image. Here I have just masked the faces because of the privacy issues. So here the camera was placed for the front view, and here the camera was placed for the top view. The data set we have collected was based on these scenarios, that there will be 4 positions in our cabin, and we have captured different activities like the no occupancies, the number of occupancies there varying from 1 to 4, sleeping, seat belt, child seat, cell phone, drinking, eating, glass bottle, etc., cigarette, e-cigarette, tools and harmful things inside the cabin. These are few glimpses of the data we have captured, that there are occupants having their luggage, they are drinking inside the cabin, they have different harmful tools or the knife, these kind of scenario. And there are some irregular scenarios as well, that we can see somebody is wearing an apparel which has a picture itself, and there may be a picture in the rear view mirror as well. So if we are talking about the object detection, these two will also demonstrate that there are 2 more person instead of these 4 person. If we just go through the object detection, then we will see that it will detect person here and there. These are the irregular situation we will focus. So, and there are scenario related to the cigarette smoking and anything else. So as we said that there is no in charge who will take care of that, for which we require the intelligent in-cabin monitoring. So I will show you. This is the scenario I have trained on object detector. So it was able to detect the person. It was able to detect the person with the accuracy of 99.934%. For the front view images, it was also able to detect the same high accuracy. It was about 99.74%. But the scenario changes as the look angle change. If we are talking about the top view, then we can see it predicts that it is a toilet with 18%. The person is only with the 13% accuracy. There are chairs. These are the results. So only by changing the view, we can see the model was not able to predict, which was earlier showing very good result. So these are the thing we should take for the irregular situation in level 5 and beyond vehicles. So, and the next problem was related to the privacy issue, which professor has told you. So we have done another work related to the privacy. So if we will, because we know that the vehicle will be the connected vehicle, and it has to share the real-time video through the cloud, real-time information through the cloud to the data center for further monitoring in terms of the behavior or intention of the passenger sitting inside the cabin. So we require to preserve the facial information for the personal privacy, but at the same time we have to capture the real-time monitoring as well in terms of object, in terms of emotion and intent monitoring. So if we mask the face of the person by mosaic or by blurring or something, we will lose the informative information which will be further required at the data center for further monitoring task. And if we send the real face, then there will be problem with the personal privacy. So we, for this scenario, we developed our own system which was capable of face swapping as well as face reenactment. Face swapping is just swapping two faces simultaneously so that we can have third face. As we can see here, there is a target video of Obama and there is a source face of Xi Jinping. And after swapping, we can see it is the third face which is neither belonging to Xi Jinping and nor belonging to the Obama. So we have swapped, but the problem is that we have to further monitor, further develop another event and emotion detection task. So only by swiping the face we cannot solve it, because we have to have the puppetering, we have to have the exactitude in our real-time video. So here reenactment is required. Reenactment is enactment in the same way how the target video was portraying. So we have to maintain the real emotion, real gesture of the face with the anonymized face. So we have to take care of both these tasks, swapping and reenactment. For this, we have developed the gain-based network, and we have demonstrated this in HCI 2020. So the concept was related to develop a set of generators. The first will be for the reenactment and segmentation, in which the generator just take the segments for the head and for the hair as well, so that we can as I was talking about the reenactment, so we can easily reenact the face and hair, because as you can see that here is one celebrity from Hollywood, and this is well-known celebrity from the Bollywood. So we can see that we have taken their segmentation of facial and hair segmentation, and then we have portrayed the face swapping and reenactment. But for him, because we can see here that this face has extra space and this face was having only this position, so the mask was related to only this, and we have to swap on this face. So there will be some portion which we require to in paint, so that we can see the entire face in our segment swapped faces. So here we can see through this inpainting generator it was able to portray that, and then blending is required to maintain the environment and other background scenarios, so that we can see the exact thing. So we have implemented this concept in our proposed facial anonymized in-cabin monitoring, and these are the results. So there are many face swapping algorithms like the Nerken et al., deepfake, and face swap gain algorithms. So these are the source images and these are the target, and these are the result for different algorithms. We can see that the FS gain was able to do this face swapping and reenactment in beautiful manner. Other than that, other algorithms are not compatible in that scenario. So this is the block diagram and the flow chart which we have developed in our own face anonymization system for the autonomous vehicle. So for the intent and occupant monitoring, we require face swapping and reenactment before the sending of the data to the data center from the vehicle. So we have applied our concept here. So these are the scenarios. These are the source faces we have chosen. These are the AI generated faces, as Professor already said, because in previous slide we have seen that there is a real person, Xi Jinping. So even after swapping, there might be problem with the identity of the source person. So to overcome that scenario, we have chosen the artificially generated source images, and there are two. Yeah, we have taken care of the look as well. We have taken care of look and gender. So we have taken care of the Eastern and Western look, and we have taken care of the gender as the male and female. So we can see the results. So for the Western look target, we have swapped the face with these source faces. Professor has already explained the scenario. We can see the base swap face was obtained when we swapped the Western looked face with the Western male. Instead, we have not got the exact result, because I told you while monitoring we require the exactitude so that we can portray the same emotion or something, because our task is to monitor for the safety and security and to preserve the privacy. Here the look was changed with the Western look, and this image has male and female both. So we can see if the face was swapped with the Eastern female, then the result was best, and for the female. But for the male, if it was swapped with the male Eastern face, the result was good. These are the scenarios which we have captured in our own data set. These are captured our own data set. So we can see the best result was when the female face was swapped with the female face and the male face was swapped with the male faces. So here the male faces are portraying the correct result. And that's all. Thank you. So this is all about the presentation demonstration from our side. I think I have gone through within the limit.
Okay, thank you so much, Dr. Mishra, and it was really very informative.
Thank you, Professor.
So I hope Professor Kim is here, right?
Yeah. We both are here.
Okay, so we need to have few discussion. Maybe we'll take few questions from audience as well. Meanwhile, okay. So what we were planning, like we can have a short discussion, panel discussion kind of thing. You both can join at that particular end, right?
You can release.
And
we can share.
okay, so just following the lectures, your like Dr. Misra's and Professor Kim's lecture. So I have let's start with the few questions, then maybe we'll discuss about it, right?
Yes.
Okay.
So Professor Kim, I have a very short question, right? Maybe you can answer it. So the very basic question, as we know, in many developing countries, it's not very easy to get a very well-defined road, right, where you can enable autonomous vehicle, right? So in many literatures we saw people are talking about the concept of flying cars, right? So how do you see the future of smart transportation from today to maybe next 10 years or 20 years? Do you think there is the concept of flying cars and other aspects will also come into the picture? What's your opinion at all?
That issue is now we are starting to.
Yeah, we are already going through that. There is payload vehicle, the autonomous drone taxi. So in Professor's slide and in my slide as well, you have seen that there is already drone taxis, which is we will see in near future, as you are saying.
So we call it for UAM, urban air transportation.
No. So the other question could arise: how you are going to manage the air traffic?
Yeah, that is actually very important issue. Actually, we are concerning for 6G.
Yes.
6G enabled the UTM. UTM is urban traffic management system. Currently, the most of cellular communication is for the base station is directed to the ground, but all the air vehicle is flying above the 100 meter to 500 meters. That range, the current cellular or the 5G is not covering this area. That we need for the satellite-based system. Then the satellite-based, the low altitude satellite is a basic component of a 6G. Then we think that in the next decade, but we in the 6G roadmap, we will be commercialized in the 2030. Then I think can be almost synchronized for UTM and the 6G new technology we're combining. Then it can be the 6G the autonomous UAM will be in the future in the next 10 years for autonomous air mobility will be. You can see, yeah. For big city, traffic is very severe. Yeah, then you can enjoy for.
So the other question. So do you think is there any need to build a dedicated lanes for the autonomous vehicles in expressway?
Actually, maybe in the beginning, but eventually, I think it can be a mixture of a human driving vehicle and autonomous vehicle. I think no need for the autonomous vehicle lane. Separate
No,
autonomous
so
vehicle.
if you take the example of many developing country, maybe if you go to the European country, right?
Mhm.
So it's very difficult to even get the lane for your car, right? People will cross from anywhere. You never know, right? From which side people are. Even in India, you'll get a lot of cows as well, right?
Yes,
You
I
never
think
know from which side
we
they will
need
come.
level
So you will always be stuck in somewhere. It's really impossible to move ahead.
I think the air will be the faster.
Yeah.
Air you can make the lane in the 3-dimensional, the layer by layer. But in the 2-dimensional, there's a limitation in space. But the air we can extend by layer, then you can obtain more lanes. Or if you your positioning and the localization technology is more accurate, you can get more lanes.
It has other advantage as well, that there will not be any pedestrian or something, so we can get rid of that as well.
No. So it's very difficult to get the. You cannot get rid of the pedestrian, right? Dr. Misra, I got to know, like, you're from ITBHU itself, right?
Yes.
So just go outside of the main campus of ITBHU and see. Do you think your car would be able to move even a single feet?
Yes. You're
Okay,
right.
the reality is another aspect, right?
Yeah, right.
So the maybe the one last question from my side, then we'll take few questions from the audience as well, right?
Okay.
So there are many beginner in our audience right now. So just give a big start. So what are the effect of AI, actually artificial intelligence, implemented in autonomous cars? So what particular direction can you give it to? Maybe for the basic, from basic to the advanced level, the person who is looking to exploit the concept of AI into the autonomous domain.
Actually, autonomous vehicle is a big platform. All kind of the AI technique for the image recognitions, for natural language recognitions, also the reinforcement, all kind of technologies are required. But there is the mandatory requirement is for the safety issue. There is there is a functional safety in the autonomous vehicle system. There is also the standard with for you call the SOTIF, safety of intended function, is for the safety criterion of artificial intelligence system. Then every in the autonomous vehicle, this kind of the safety is applied in addition to the normal the AI for the mobile phone and the other commercial application. That's why eventually I think the AI for autonomous vehicle is for the top the state of art technology.
It has become this synonymous thing, like computer vision. Earlier it was there, but nowadays any kind of video and image processing task is synonym to the autonomous vehicle, I think so. In terms of image process, artificial intelligence based image processing, it is the synonym of the autonomous driving itself.
No, but there is slight variation as well, right? If you see the concept of latency is not pretty much important when you're going to talk about the image processing and the car set. But in autonomous vehicle, latency and accuracy is pretty, like, they play a very important role, right? We cannot rule out the quality requirement and accuracy at the same time, right?
Exactly.
So even a certain
fraction of second or millisecond is
it may be dangerous for anyone, right?
Right.
Yeah.
So let us take few questions from audience side. I can see one question. Rudransh, you can directly ask your question, right? You can mute yourself and ask your question to the professor.
Yes, sir. So can I ask now?
Yeah, you can.
Yes, sir. Good morning, sir. So I have a question, like, regarding what you think about, like, the technique of MITs, like self-driving car, like the way they are collecting the data from a 3D simulated environment, and that 3D simulated environment is with for cancer cells. And then they are using reinforcement learning in that 3D simulated environment, collecting the data, collecting the different type, collecting the data, and then using that data. They are then using that data to train their self-driving cars neural network, and then they're using on the real life scale. Like if this approach is so efficient, and like why other companies like Tesla and other institutes that are making self-driving car, why they aren't using these techniques? Is this technique actually efficient? So
Professor Kim, did you understand the question, or should I explain it?
Asking that there is some simulated environment data set and real environment data set.
Okay.
So is it good to go with the simulated environment data set or with the real environment?
Then usually in my slide, we are the pre-training phase, in the final training phase. Usually we use a simulator for the pre-training, but for the actual implementation on the real vehicles, the simulation cannot consider all the possible situation, and then the image quality, and there are many different things. Then simulation only provides the validating the initial model, but the final the validation we need to validate in the real vehicles. Then for simulation, most of the paper and the academic research is about the limitation of budget and the limitation of time. Then we are doing usually on the simulation, but for real implementation, we need for a lot of the investigation on the real vehicles.
I would like to add that, as you said, the two scenarios, the MIT is the academic institution and Tesla is for the commercial and industry platform. So as professor said, that the thing is, in simulated environment, you are saving the cost of collecting the data set. If you have industry to collect it, because data set collection is very huge task and it requires very much amount. So for academician, it is not means feasible to implement such a huge investment. But Tesla can do the same thing because it has their own platform. Several vehicles they can implement the onboard equipment for collecting data sets. So they can do. But as professor said, that safer way is to go first with the simulated environment, because there you can collect data set in simulated environment without any huge amount of investment, and then just retrain, as you already told that MIT is going for that. Everyone, I think in academics, it is the better way. Use both. First collect data set from the simulated environment and then retrain in the real environment the exact model you are asking about. I think...
So maybe
yes,
I will also add one more concept into it, right? So in the simulation environment, you can crash your car as well, right? It is not going to be any problem. But in reality, if you are going to crash your car, it would be very dangerous, right? Okay.
So like one more question I have, in relating to this. So what do you think about the technique of reinforcement learning that they are using? Like instead of using like a simple CNN or then other combination of other neural networks, like how they are combining the reinforcement learning with like computer visions.
Yeah, for reinforcement learning is for, that the supervised, unsupervised, reinforcement is three main category of learning. But that currently the reinforcement learning are facing a lot of the problems. I don't have enough time. I don't think I have enough time for explaining what the details of reinforcement learning. Right now, we are challenging new the learning technique, the beyond the reinforcement learning. The supervised, unsupervised, the reinforcement learning is a method in the textbook. Then in the real world, there's a more advanced approaches. So right now it's going on. Then basically the simple reinforcement learning or the unsupervised, supervised learning cannot solve the complex problem in the real environment. That's why there are many new ways. And then there are the many shortcomings of reinforcement learning itself. Then you can solve a very static problem very efficiently, but for the dynamically changing problems, or rules are changing. There are many the unseen environment conditions. We facing this kind of situation in real world, but reinforcement learning cannot solve this kind of problems. That's why we are learning method. New learning rule is another area of research.
Yeah.
For then also the autonomous vehicle and the mobility is very important for this kind of new learning way. Because of static learning, we have a lot of data itself, but autonomous vehicle is it goes very dangerous in real environment, the real experimental situation. That's why we are very careful, and we need more the learning method for the autonomous vehicle. That's why it's autonomous vehicle, as I told you, it will be new platform. It's for leading the AI technology to the new way of the algorithms or new way of learning method.
That's right. That's right. And now I think it's in the initial phase, it's impossible to capture all the aspects, right? You might be trained, means maybe system is trained with the different kind of aspects. Maybe you trained your system with the buffalo, with the cows, but with what? But what happens if goat is coming in on the way, right? That is another aspect. So we need to make our system more intelligent, but it's iterative process. We cannot do everything within one shot.
Yeah.
Right. So we have few more questions, but we are lagging with time. So maybe I will just go and thank to everyone. So dear speakers, attendees, and staff of teaching, learning, and team IIT BHU specifically, thank you so much. On behalf of coordinator Dr. N.S. Rajput and IIT BHU Varanasi, I, Dr. Ajay Pratap, co-coordinator of this program, would like to convey my sincere gratitude and thanks to everyone for being the part of this program. We have been together for last almost 6 days, and specifically today is the day to be thankful and to be inspired. First of all, we must be thankful to our renowned speakers from around the globe and finding a time for us from their busy schedule. Here in this short-term course, we have received a great learning platform to apply in our research objectives for betterment of societies. Dear attendees, now if you can notice, I would like to know that what a gift it is to be as renowned speakers from academia as well as industry, because not all short-term course offers such an advanced version of deep structured topics. I am also thankful to Cisco India for their cooperation and coming together for this short-term course, and I strongly believe that your support will always be with us in the future as well. Finally, I would like to thank the staff of teaching learning team IIT BHU Varanasi for being here from last 6 days, even above all being in the time at the at the weekend, especially when the Holi is knocking at the door. Okay, I want to extend my generous thanks to the entire team for their support and cooperation. Thank you, everyone, and may this festival for colors filled with colors in your life. To every shade of you, I wish happy and colorful Holi. Thank you so much for being here, and happy Holi once again. Thank you so much.
Thank you, Professor.
Thank you so much. Okay, bye bye. Thank you, Professor Kim. Thank you for your time and cooperation as well.
Thank you very much.
Yeah, thank you so much. Bye bye.
Happy Holi to you all.
Thank you so much. Bye.